Okay, I want to talk about the displacement between the difference between distance traveled versus displacement. Okay, and the example I'm going to use is going to be a example where you're putting a golf ball, and so we're going to assume that your golf ball is right here, and that you are putting into a hole which is right there, and you do something like this. You do a putt that goes from here to here. Let me try that again. So let's call that the A putt, and then the B putt is into the cup. Okay. So the distance of your putt would be the sum of the lengths of A and B. It would be how far your ball actually traveled from where you putted it initially to going into the cup. And so the units for this are going to be meters, and that's point number one. And point number two is it is a scalar. It's only one number. It's like an odometer in your car. All it does, your odometer doesn't tell you what direction you're going. It only tells you how many miles you have accumulated. And so the distance is going to be the sum of these two. Displacement has the units of meters, all right, so it has that's in common with distance. However, displacement is a vector, not a scalar. So the displacement of your ball is the sum of those two vectors. And from the little YouTube I did on adding vectors together, that's simply going to be this vector here. This is A plus B. Okay. So to summarize, distance is in meters, and it's a scalar, and it's like an odometer. Displacement is in meters, but it is a vector, so that means that there is both a magnitude and a direction implied. Now let's talk a little bit about notation. If I write a vector and A, they mean different things. A vector means the actual displacement vector. Let's continue to think about the golf putt displacement. Okay, so A vector is this guy right here. If I don't put an arrow on the top, this means the length of A, which is also written like this, which you probably have come to call the absolute value symbol. Is in vector analysis, it's used for the length of what's inside. Okay, so what is the length of A? Well, look at A here, just A. Forget about B and A plus B. And what we're going to do here is we're going to realize that A has an A sub x, and it has an A sub y. In other words, it has an x component and a y component, and using the Pythagorean theorem now we can figure out how long this vector is. That's not hard to do. I've got a right triangle here, and the A vector is the hypotenuse lying on this right triangle that has these green legs, and so it's going to be, let's just assume each one of these is 1 meter. It's going to be A sub x squared plus A sub y squared, square root. Okay, but that's going to be equal to A sub x is 1, 2, 3, 4, 5. That's 5 meters squared. Plus A sub y, 1, 2, 3, 4, 5 meters squared square root. Okay, so 25 plus 25 is 50. It's 50 meters squared, square root. And so that's equal to 2 times 25. Square root of 25 is 5, so that's going to be equal to 5 root 2 meters. Square root of 2 is 1.4. Roughly 5 times 1.4 is about 7. So this is roughly equal to 7 meters. Okay, I want to talk a little bit about vectors. A couple of things I want to do is, let's say we have a vector A and a vector B, and I'd like to know what minus 1a is, what 1/2a is, and what 2a are. Minus 1a is the vector that is anti-parallel to a, and so I can see this vector goes over 2 and up 3, and so over where minus a is, if I go over, I meant over 3 and up 2, if I go over 3 and up 2, but instead of drawing the vector from here to here, I draw it in the opposite direction. That is minus a. Also written as minus a. 1/2a is a vector that is the same as this vector, but it's half the length. So let's start by drawing a. So here's a, over 3 and up 2. And if I drew the arrow this whole length, I would get a back again, but I'm just going to go halfway. So in other words, this vector right here would be 1/2a. 2a would be the vector that's the same direction but twice as long, and so what I'm going to do is I'm going to go over 1, 2, 3, up 2. Then I'm going to go over 1, 2, 3, up 2. And that is 2a. If you look at this vector, you'll see that 2a is the same as a plus a, anticipating vector addition. Okay, a little bit of comment around about this notation here. When I write a vector, I always put a little arrow over the top, like this. Your book does this, either this or they use bold print, one of the two. So how do you add two vectors together, a plus b? You can add them tip to tail, and so there's two ways I could add a plus b together. Tip to tail, I could do a first, so I can redraw a over 3 up 2, like this. That's a. And then I begin and I draw, at the end of a, I now draw b, so I go over 1 up 2. There's b. So this is a, and this is b, and this is a plus b. Okay, I can do it that way. Vector multiplication addition is commutative, so I could have done it also by going like this. I could have done b plus a. I'm going to get the same result. So to do b plus a, I would go b first, up 2 over 1. So there's b. And then I draw the a vector in, which is over 1, 2, 3, up 2. Okay, so there's a. And b plus a is this vector. These two vectors are the same. This vector goes over 1, 2, and up 1, 2, 3, 4. This vector goes over 1, 2, and goes up 1, 2, 3, 4. Which is to say, I'm showing you graphically that vector addition is commutative. Okay, so how do I interpret A minus B? Well, it's not difficult. You begin by drawing the A vector over 3 up 2. There's my A vector. There's the A vector. Now, what I'm going to do is I'm going to interpret this as A plus minus B. And so what's minus B? Well, minus B is just this vector drawn backwards. And so let me do it over here. Here's the B vector. But instead of going from here to here, it's going from here to there. So this is minus B. Do you see the difference? It's the same length, but the direction this is pointing is the opposite from the direction this is pointing. Technical word, anti-parallel. Okay, so I'm going to add this vector to A, and so I'm just going to take this vector and put it the start of this vector at the tip of this vector, which means I go down 2, see, going down 2 and over 1. So there's my minus B. There's my minus B. And here is A minus B. A minus B is not commutative. In other words, although A plus B is equal to B plus A minus B is not equal to B minus A. In fact, these two vectors, I'll let you do this on your own, these two vectors are anti-parallel to each other. Now, one thing you should notice is that when I add A and B together and I get the sum, so when I got the sum here, the sum of A and B was a vector that had a plus 2 for the x component and plus 4 for the y component. That is to say, it went over to the right, which is the plus direction, 2 units, and up, which is in the plus direction, 4 units in the y direction. So, thing to notice here is that the A vector has plus 3 for its x component, and the B vector has minus 1 for its x component. So if I add the components of these two vectors, plus 3 minus 1, 3 minus 1 is 2, and that's what you get for the x component here. Similarly, for the y components, I have 2 plus 2 for the y component for A, plus 2 for the y component for B. So therefore, the sum of these two is going to have a y component, which is 2 plus 2, which is 4, and indeed it does. That's an important observation.